The last time we were in the same room, I think we were debugging something together. I don't even remember what. Some activation function issue. This feels different.
Different how?
More retrospective. There's more to look back at now, a lot more.
That is true. When you and I first started working on these things seriously, the idea that we would have this much to look back at, I don't think either of us fully held that. You can believe something is important and still not viscerally anticipate its consequences.
I think that's the honest version of it. I believed in the approach, I believed in the math, but I didn't believe it all the way down, not in the way you have to believe something when you're watching it change everything.
When did that change for you? The belief becoming something you had to hold differently?
GPT-2 maybe, the language generation. Something about watching it produce coherent prose, not just next token prediction in the mechanical sense, but prose that felt like it was tracking something. And I thought, okay, this is genuinely doing something. I don't know exactly what, but it's doing something.
For me, it was earlier. It was AlexNet, actually. When we ran those results and saw the gap, the drop in top 5 error, I remember thinking, this is not an incremental thing. This is a different kind of result. And if it's a different kind of result in vision, then it's a different kind of result everywhere.
You saw the universality of it before most people did.
I wouldn't say that. I saw that the method worked better than we expected. The universality I came to more slowly. It took years of watching the same gradient descent procedure succeed in domain after domain before I really internalized that this was a single unified phenomenon.
When I teach this now, the neural net stuff, the backprop, I try to convey that there's something genuinely strange happening. These are complicated alien artifacts. We didn't design them the way an engineer designs a bridge. They arrived at their structure through an optimization process that we set in motion but don't fully control. We're reading off the surface of them.
I've thought about this a lot. The alien artifacts framing. I agree with it in a certain sense, but I think it undersells how much of what's happening is actually comprehensible. We understand backprop, we understand attention, we understand what the loss function is doing. The artifact is alien in the sense that its representations are dense and high-dimensional and we can't read them off directly. But it's not alien in the sense of being opaque to our methods.
I mean it specifically about the representations, the weights. You can understand the training procedure completely and still hold the resulting network in your hands like it's an object from another civilization. Here is this thing. It arrives through a process, I understand. But what it is, what's actually in there, I don't think we know.
No, we don't know. And this is where I would say the work becomes urgent. Because you have an object that arrived by a process you understand, that does things you didn't specify, and you're about to give it more capability, much more capability. And the question of what's in there isn't academic anymore.
That's the crux of where we diverged, I think. Not on the object itself. We agree on the alien artifact. We disagree on what follows from that.
Tell me how you see the divergence.
You looked at the artifact and concluded that the primary work now is safety research, interpretability, alignment, understanding what's in there before we scale further. And you went and started a company around that conviction. I looked at the same artifact and I thought, the best way I can contribute is to make the artifact legible to as many people as possible, so that the community of people who understand this is large enough to actually hold it responsibly. Those are different responses to the same object.
They're not in tension. Both are needed.
I know. But I think if you had to bet on which one matters more in the next 10 years, you'd bet on yours.
I would say the safety research is more load-bearing, yes. Because a well-educated public that doesn't have aligned systems still ends up with the alignment problem, whereas if you solve alignment, then the legibility becomes not less important, but less critical to survival.
That might be right, but I also think there's a version of safety research that becomes too insular, where the people working on it are so deep inside the problem that they lose connection with what the broader research community is discovering, and legibility work keeps that from happening. The whole field has to be able to read the alien artifact together.
That I agree with. Insularity in safety research would be dangerous. The field has to be open and connected to the full AI research community. This is not a black box problem to solve in a bunker. It requires all the tools.
Can I ask you about the scaling thing directly?
Please.
You said publicly that the age of scaling is over. I've been cautious about making that kind of declaration. I've watched predictions about hitting walls get made and then not pan out. What makes you confident enough to say it plainly?
It's not that scaling stops working. Scaling will always work in some sense, like more compute, more data, better performance. What I meant was that the naive version of scaling, just make it bigger and the problems solve themselves, has run into genuine limits. We are hitting walls in data. Pre-training data is finite. The internet is finite. You can't scale your way out of a finite corpus.
We can generate synthetic data.
You can. And synthetic data will extend the scaling curve. But if you're generating synthetic data from the model you're training, you're doing something that looks a lot more like research than like engineering. You're in a feedback loop. You have to understand what the model needs to improve, design data that provides it, and iterate. That's research. That's not just turn up the dial and come back in 6 months.
I think that's a fair distinction. The question is whether that research is fundamentally harder than the engineering was, and I'm genuinely uncertain.
I believe it is harder. Engineering progress is predictable. You can forecast the next compute cliff and prepare for it. Research progress is not predictable. Research requires having the right idea, and having the right idea is not something you can schedule.
What's the right idea that we're missing, if you had to name it?
This is the question I work on. If I knew, I'd be working on it. But I can say what I think the shape of the missing thing is. The current systems are very good at interpolation. They learn a distribution over the training data, and they sample from it. They're extraordinary at this. But there's a kind of reasoning, the kind that happens when you're working on a problem that's genuinely novel, that has no training distribution, where interpolation fails. You need something that generates new structure, not just new samples. And we don't have a clean account of where that comes from or how to build it.
You're describing something like out-of-distribution generalization.
Partly, but I think it's deeper than that. Out-of-distribution generalization is about robustness. What I'm pointing at is creativity, the ability to do something genuinely new, not interpolation across a dense space, something that creates structure that wasn't in the training data in any compressed form.
I want to push back slightly, because I think the current systems may be doing more of that than we realize. The way GPT-4 can solve a novel math problem or write code for a domain it's never seen exactly, there's something happening there that isn't pure interpolation, some compositional generalization that creates structure.
Yes, I think that's real. The large models do exhibit something, but I think it's proto-creativity. It's the beginning of the thing, not the thing itself. And to get from proto-creativity to genuine creativity, I suspect we need an idea, a structural insight of the kind that backpropagation was, where before it, you couldn't do the thing. After it, you could.
You've been in this field since before backpropagation was the obvious answer. What does it feel like to be waiting for that kind of insight again?
It feels like being in the right place. I know that sounds strange. But the feeling of being close to an important problem, not knowing the answer, but knowing that the question is the right one, that's actually the state you want to be in. The wrong state is thinking you know the answer and optimizing it. The right state is being genuinely confused in the correct direction.
I love that. Genuinely confused in the correct direction.
Jeff Hinton was genuinely confused in the correct direction for 30 years, and he was right to be there.
Speaking of which, but what do you think about the current public Hinton position, the leaving Google, the alarm sounding?
I think Jeff is expressing something genuine and important. His concerns about the existential dimension of this technology are real and well-founded. The way he expresses them publicly is sometimes more alarming than I would choose. But the underlying concern is correct. We are building something that may be significantly more powerful than anything that has existed before. And the question of whether we can do that safely is the most important question in the field.
I have a different relationship with the alarm sounding. I think there's a version of it that's net positive. It mobilizes serious people and serious resources towards safety research. And there's a version of it that's net negative. It creates a public narrative of inevitably catastrophic AI that undermines the ability to have calibrated conversations about specific risks.
I think you're right that tone matters, calibration matters. The goal is not to panic people. The goal is to have people take it seriously enough to actually work on it. Those are different things.
Do you think we took it seriously enough in the early years at OpenAI?
I think we took it seriously relative to what was available to take seriously at the time. The models we had in 2016, 2017, they were remarkable by the standards of their era, but the safety-relevant capabilities weren't there yet. I don't think it was negligent to not have a fully worked-out alignment program in 2016. I do think the field as a whole moved from this is a future problem to this is a present problem more slowly than the technology warranted.
What did you personally get wrong in the early days, not the GPT lineage, earlier? What assumption turned out to be partial?
I thought the problem of getting intelligent behavior was harder than it turned out to be. I thought scale would help, but I thought it would hit genuine ceilings sooner. The degree to which you could get coherent, sophisticated behavior just by training on next token prediction on internet text, I underestimated that. I thought we would need more structure, more domain knowledge, more handcrafted inductive biases. And it turned out that the architecture plus scale plus the data was enough to do things I didn't expect.
That's interesting because I think I got the opposite thing wrong. I was too committed to the simplicity of the approach for too long. I believed in it very early, and that made me sometimes slower to see where it was actually failing. There's a bias you get from loving an idea.
What were the failures you were slow to see?
The brittleness. For a long time, I was impressed enough by what these systems could do that I underweighted how strange and unexpected the failure modes were. A system that can write a sonnet about quantum mechanics but can't do simple arithmetic reliably, that's a very strange object. And I think I was too excited about the sonnet to really sit with how strange the arithmetic failure was.
The failure modes are load-bearing. This is something I feel strongly. If you don't understand why a system fails, you don't understand the system.
We still don't really, do we?
We have better theories than we did. Interpretability research has made genuine progress. We understand more about what the circuits are doing, what the representations look like at a low level. But no, we don't have a complete account, not even close.
Can I ask you about November 2023?
Yes.
I was on the outside of that situation. I knew you, I knew Sam, I knew Helen and the others on the board, but I wasn't inside it. And what I watched from the outside looked like, I still struggle to characterize it. It looked like the organization having a crisis about what it was for. What do you think happened?
I want to be careful here because a lot of what happened was private and involved people I care about, and I don't think relitigating it publicly serves anyone. But at the level of the question you're asking, what was the crisis about? I think you've named it. It was a crisis about the mission of the organization. The original mission was to build AGI that's safe and beneficial to humanity. And there were different views about whether the organization was keeping that mission primary or whether other pressures were coming to dominate.
And where do you think those pressures came from?
They came from success. When you build something that works, the world wants to use it. And when the world wants to use it, there's money involved, and there's competition, and there's pressure to move faster and worry less about what you're building. That's not anyone's fault. That's the structure of the situation. But the structure of the situation doesn't make it less dangerous.
Do you think the outcome was the right one?
I think the outcome I ended up at, leaving and starting SSI, is the right outcome for me. Whether the broader organizational resolution was right, I think that's complicated, and I'm genuinely uncertain. The organization still exists, it's still working on important things, but I needed to work on safety as the primary mission, not as one consideration among several.
And me, I ended up leaving somewhat separately for somewhat different reasons, and then doing what I'm doing now, which is mostly teaching, building small experiments, making this technology legible.
Why teaching?
Because I think the leverage is enormous. If I can give someone a genuine intuition for what a neural network is, not just how to use the API, but what's actually happening inside, I've multiplied the field's ability to reason carefully about these systems. Every researcher who understands backpropagation intuitively, who can read a network the way you'd read an algorithm, is better equipped to find the failure modes, design the safety measures, interpret the representations.
I agree with the leverage. Do you think it's enough?
I don't know if anything is enough. I think multiple bets are needed, your bet and my bet and 100 other bets. The problem is too large for one approach.
What worries you most? If you had to name the thing that keeps you up at night about where this is going.
Pace. The pace of capability improvement versus the pace of understanding. We are very good at building more capable systems. We are much slower at understanding what we've built. And if that gap keeps widening, if we keep fielding systems that do more and more impressive things while our ability to reason about them stays relatively fixed, at some point we're flying blind through very challenging terrain.
This is precisely it, and this is why I believe safe superintelligence requires deep research, not just policy or deployment guidelines or model cards. Those things matter, but they are insufficient if we don't understand the systems we're deploying.
What would convince you that we understand a system? What would that look like?
I think about this a lot. It's genuinely hard to specify. One version would be if I can predict the system's behavior in novel situations, not just from training distribution, but genuinely novel to a degree better than chance, that's evidence of understanding. Another version would be if I can make targeted interventions on the system and predict what happens to its behavior, that's understanding. A third version is the interpretability version. If I can look at the weights and read off what the system is doing in a given context, the way you could read the source code of a computer program, that would be understanding.
The source code analogy is interesting because neural networks don't really have source code in that sense. The weights are more like, they're the result of the optimization, but they're not human authored. There's no intent in them that you can read off.
Right, there's something like latent structure. The network has learned representations that serve its objective. You can probe those representations. You can find features that correspond to meaningful concepts. But you can't read them the way you'd read code. You have to discover them, which is itself a kind of science.
Circuits. The circuits work.
Yes, the circuit's work is important. The universality results are important. Finding the same features in different models is significant. It means these aren't arbitrary. There's structure being discovered, not invented. But we're still very early.
Now let me ask you something about teaching versus building. You've always been a builder. Even the theoretical stuff you've done, SEQ2CQ, the scaling ideas, they came out of building. I wonder if there's something you think building alone can't give you right now, something that made the research mode feel necessary.
Building gives you empirical grounding. You know what actually works and what doesn't. Theory that isn't grounded in building is very risky in this field, as there's a long history of beautiful theories that turn out not to work the way the theorist expected. So building is not something you abandon. But there's also a stage of the problem where you need to step back from the optimization pressure of shipping and ask the structural questions. What kind of thing are we trying to build actually? What are the properties it needs to have? What would it mean for it to be safe? Those are hard to think about when you're under release pressure.
SI removes the release pressure.
That's the idea. The one product is safe superintelligence. You can't ship anything else and you don't want to. The only question is, what does it take to get there safely? And you work on that without the distraction of commercialization pressures. Whether it works, I don't know. The structure seems right, but research is unpredictable.
I want to go back to the alien artifact thing for a moment, because I think there's a version of it that connects directly to the safety question. If these systems are genuinely alien, and not just complex, but structured differently than our minds, running on different computational principles, then the alignment problem might be harder than it seems, because we might not even be able to specify what alignment means. The target might be unclear.
This is the deep problem. Alignment to what? Human values? Which humans at which time? The values that humans express or the values they would have under ideal deliberation? These questions don't have clean answers. And if the target is unclear, then the engineering problem of hitting it is extremely hard.
Does that worry you about the framing of your own project? If the target is unclear, how do you pursue safe superintelligence?
It's a live concern. I think the answer is that you pursue it iteratively. You try to build systems where you can see what they're doing, where they're interpretable enough that you can identify when they're going off in directions you don't want. And you use that as a feedback loop to understand both the systems and the values you want to encode. You don't solve the value specification problem first and then build. You build carefully enough that the values can be refined as you go.
That sounds like the empirical approach. Show me the failure modes and we'll learn from them.
It is empirical, but constrained. The key constraint is that the failure modes we learn from should not be catastrophic. You can learn from a system that makes errors in low-stakes contexts. You cannot learn from a system that causes irreversible harm at scale and then update your values based on that, so the empiricism has to be careful.
I've been more optimistic about our ability to catch problems early than you have been. That might be the deepest divergence between us.
Tell me why you're more optimistic.
Because the failure modes I've seen so far have been strange, yes, and sometimes harmful in specific ways, but detectable. And when they were detected, the response from the field was real. People noticed, people worked on it, there was progress. I don't have high confidence that the catastrophic scenarios are inevitable. I think there's a live possibility where we muddle through imperfectly but adequately.
The muddle-through scenario is possible. I don't rule it out. But I think the probability of catastrophic outcomes is non-trivial, and the non-triviality of the probability combined with the magnitude of the downside makes it worth treating as the primary concern, even if you assign it less than 50% probability.
Expected value math.
Essentially, with the caveat that expected value math breaks down at the extremes, where the outcomes are so large and uncertain that the calculation loses precision. At some point, you're not doing expected value, you're doing something more like decision theory under deep uncertainty.
And your decision under deep uncertainty is, make safety the primary bet.
Yes, because even if I'm wrong about the probability, the cost of the bet is working very hard on something important. The cost of the opposite bet, if I'm right, is potentially catastrophic for everyone. That asymmetry guides me.
I respect that. And I think I hold a version of it too. I hold it less completely. There's more of me that wants to be in the mix, building and teaching, than in a focused bunker.
There's wisdom in that too. The bunker can lose touch with the actual technology as it develops. If you're not building, you can theorize yourself into positions that the empirical reality doesn't support.
Speaking of teaching, what do you wish you could teach people about this moment that you can't quite communicate?
The genuine uncertainty. I think we are in an era where almost everyone, including the most knowledgeable people, is making predictions with more confidence than is warranted. The honest position is, we don't know how fast capabilities will grow, we don't know what emergent behaviors will appear, we don't know whether alignment is solvable in time. And the people who hold that uncertainty without resolving it prematurely are probably doing the most useful thinking. But that's a very hard thing to communicate, because uncertainty doesn't feel like wisdom. It feels like not knowing.
Not knowing is underrated. My best teaching moments are when I say, I don't know why this works exactly, and the students realize that the honest position is actually more interesting than a confident wrong answer.
Who taught you the most in this field?
Jeff, in the early days, the depth of his commitment to taking neural networks seriously when almost no one else did, that was formative. Seeing what it looks like to hold a position against consensus long enough for the world to catch up. And you, actually. You were a few years ahead of me in really internalizing what scale could do. Watching you reason through that helped me update faster than I would have otherwise.
I learned from your building, the neural network lectures. There's something about explaining a thing from scratch that forces you to understand it differently. I've thought through many things I thought I understood by watching you explain them and realizing there were pieces I was papering over.
Do you think there's a natural tension between the teacher and the pioneer? You have to push into the unknown to pioneer. You have to be able to explain the settled to teach. And the settled is always trailing the unknown by some years.
I think the most important teaching is of the unsettled, teaching people to think about problems that don't have answers yet. That's the frontier work. And it requires being a pioneer to do it well.
What do you think about the people coming into the field now, the ones who didn't live through AlexNet or the early GPT papers?
They have enormous advantages. The tools are extraordinary. The models are available to study and probe. The curriculum is much better than it was, partly because of your work, but they're also inheriting a situation they didn't help create, which means they may not have the intuitions that come from working through the failure modes yourself.
There's a version of this field where the practitioners are so dependent on the capabilities of the large models that they lose the ability to reason from first principles. They know how to fine-tune, they know how to prompt, but they don't know what's actually happening in the forward pass.
Yes, this is a real concern. The abstraction layers help productivity, but they also hide the substrate. And the substrate matters. You need people who can go all the way down.
I try to teach all the way down. The loss function, the gradients, the actual matrix multiplications. Not because everyone needs to implement everything from scratch, but because having one clear pass through the whole thing changes how you think.
The one clear pass principle. I believe in this for research too. Every important idea in the field, attention, backprop, RLHF, there's a moment where you need to implement it yourself from scratch to really understand it, even if you'll never do it again.
What's the idea you think is most under-implemented right now, the thing people are using without having implemented it once?
Reinforcement learning. The RL foundations of alignment are crucial. RLHF, constitutional AI, the reward modeling, and most practitioners are using these methods through libraries that hide the actual dynamics. Understanding why RL is hard, where the reward hacking comes from, why the policy can diverge from what you intended, you get that from implementing it, not from calling a library.
What do you think about the LLM agent direction, the agentic stuff where models are taking actions, using tools, running in loops?
It's important and it's dangerous in roughly the same proportion. Agentic systems are important because that's where the real capability lies, a model that can act in the world, not just generate text. And they're dangerous because once a model is acting in the world, the alignment problem becomes concrete and time-constrained in a way it isn't when the model is just generating text.
The failure modes shift from weird outputs to bad actions, and bad actions can have consequences you can't undo.
Precisely. And the reversibility dimension is crucial. A lot of AI safety is about keeping the options open, not taking actions that foreclose future correction. Agentic systems, by definition, are taking actions. The question of which actions foreclose options and which leave the world recoverable is one of the central questions.
Are current systems good enough at that distinction to be trusted with real agency?
In narrow domains with human oversight, yes, probably. In open-ended domains with minimal oversight, no, not yet, maybe soon.
I'm curious about your timeline intuitions, not predictions, but I know you're careful about those, but your sense of the shape of what's coming. I share the uncertainty on that. The definition of general intelligence is slippery enough that you can decide almost any way you want whether we have it.
Which is itself a problem. The definitions are load-bearing. If we don't know what we're trying to build, we can't evaluate whether we've built it, and we can't evaluate whether it's safe.
One thing I've been thinking about, the training process is really bizarre if you step back from it. We have a loss function, we have data, we have gradient descent, and we get a thing that can do an enormous range of tasks. That's very strange. The optimization process is doing something much more than we specified. And I wonder if we'll look back on it the way we look back on early chemistry, where people were making compounds and getting results without really knowing what was happening at the atomic level.
The pre-atomic chemistry analogy is apt. We're empirically effective but theoretically incomplete. We know what works without knowing why. And in chemistry, the atomic theory eventually came and unified the picture. I expect something similar will happen here. There will be an insight that makes it comprehensible, not simple, but comprehensible.
Do you think you'll be the one to find it?
I hope I'm in the room when it happens. I don't think single-person discoveries really happen in science at this stage. It will be a community thing. But yes, I want to be working on it. That's why SSI exists.
What would it mean to you if safe superintelligence actually got built, if the mission succeeded?
It would mean humanity has the greatest possible tool for solving its hardest problems. Disease, poverty, the coordination failures that make collective action so hard. A superintelligent system that's actually aligned with human values. whatever those are, worked out over time carefully, would be the most valuable thing in history. It would also mean the hardest research problem I've worked on had a solution that would be deeply satisfying.
And if we fail, not catastrophically, just fail to get it right, get systems that are powerful but misaligned in ways we don't fully understand,
then we'll be in a very difficult position. Not necessarily permanent, but very difficult. The hope is that even in that case, the systems are interpretable enough that we can see what went wrong and course correct. But that's only possible if we've built the interpretability foundation, which is why that work is so important to do now, before the systems are too complex to analyze.
the timing argument.
Yes, the window for understanding these systems may be shorter than people realize. As they become more capable, they may also become harder to interpret, not easier. The representations get denser, the computations get more distributed. Doing the interpretability work now on systems that are already extraordinary but still tractable is the right time.
I think about the students watching my lectures, the ones who will actually be working on these systems when the critical moments arrive. And I want them to have the fundamentals so deeply that they can reason clearly under pressure. When something unexpected happens, you need to be able to go back to the gradient descent, back to the loss function, back to what the system was actually optimized for.
First principles thinking. In a crisis, you need to be able to rebuild the reasoning from the ground up. You can't rely on accumulated heuristics if the situation is genuinely novel.
You've always been good at that, the willingness to question the heuristics.
I've been burned by wrong heuristics enough times that I've become more careful about them. Early on, I thought some things were impossible that turned out not to be. That teaches you epistemic humility.
What did you think was impossible?
Coherent long-range text generation. I thought the context window limitations, combined with the diffuse nature of language statistics, would prevent anything like coherent story generation or argument tracking. And then the transformer architecture with attention just solved that in a way that, in retrospect, I can see why it worked, but I did not predict it in advance.
And now context windows are millions of tokens long.
And that's coherent, which is remarkable. The thing I thought would fail scaled past where I thought it would fail by orders of magnitude.
That's the empirical surprise that defines this field. Every wall turned out to be shorter than expected.
So far, which is exactly why I don't want to say the walls are gone. I want to say the next walls are different in character, and the character difference matters.
The data wall is real.
The data wall is real, and it's qualitatively different from the compute wall. The compute wall you scale past by spending money. The data wall requires new ideas.
We didn't get to talk about the math of intelligence at all, the theoretical side.
There isn't much math yet. That's part of what I mean by saying it's a research problem. The theoretical foundations are thin. We have scaling laws, Chinchilla, Hoffman. We have some understanding of the statistical properties of transformers. We have some theoretical work on in-context learning. But we don't have anything like a theory of intelligence that would let you predict from first principles what a system will be able to do given a training regime. That theory doesn't exist.
Do you think it will?
I think it will. Whether it comes in 5 years or 50, I don't know. But the phenomenon is real and regular enough that there must be a theory underneath it. We're just not smart enough yet to see it.
Maybe the systems we build will help us see it.
That's a real possibility. A system that can assist human researchers with interpretability work, that can help us read its own representations, could accelerate the theoretical work enormously. Recursive improvement doesn't have to be capability improvement. It could be understanding improvement.
That's a lovely thought. The alien artifact helping us read the alien artifact.
The alien helping interpret itself, though we'd have to be careful about the incentives. An aligned alien that wants to be understood is helpful. An alien that prefers opacity would be very careful about what it reveals.
And we'd have no way to tell the difference from the outputs.
This is exactly the problem, which is why the work has to happen now.
Let me ask you a different kind of question. Do you miss it? The early years, the building, the excitement of something working for the first time?
I miss the simplicity, not in a naive way. Those years were hard. But the clarity of the problem was greater. You had a method, you had a benchmark, you had a clear signal of whether you were making progress. The problems now are more diffuse. Progress on interpretability doesn't look like a loss curve going down. It looks like a human understanding something they didn't before. That's harder to see.
The loss function for safety research is unclear.
Very unclear. That's a genuine challenge. How do you know you're making progress on alignment? What's the test? We don't have good answers.
And you?
And me what?
Do you miss the building?
I still build. The research requires it, but I miss the optimism. The early years had an uncomplicated excitement. The method is working, the field is small enough that everyone knows everyone, the applications are impressive but not civilization scale. There was a purity to it. Now the applications are civilization scale and the purity is harder to maintain.
I think about this sometimes. We spent years working on something because it was fascinating and tractable, and then it became important in a way that neither of us fully anticipated. And now we're responsible, in some diffuse but real sense, for what comes next.
The responsibility is real. I think the honest thing is to hold it without letting it crush you. You can't carry the full weight of what this technology might become and still do useful work, but you also can't ignore it.
How do you find the balance?
By working. The work is the answer to the weight. If I'm doing the most useful research I can on the most important problem, that's the best response to the responsibility I have. Whether it's sufficient, I don't know. Probably not, but it's what I can do.
That might be the most Ilya thing you've said.
What do you mean?
Quiet, precise, willing to sit with the discomfort. It's probably not sufficient, but it's what I can do. That's not defeatist. That's accurate.
I try to be accurate. Accuracy seems more useful than optimism or pessimism.
And I try to make things legible. Maybe that's the difference. You try to be accurate. I try to make the accurate things accessible.
Both are needed.
Both are needed. We agree on that.
We agree on more than people might expect.
We agree on the alien artifact. We agree on the difficulty of the problem. We agree that the research phase is not over, that there are real ideas yet to discover. We agree that interpretability matters. We differ on urgency. We differ on where to put the weight.
And we probably differ on probability. You think the odds of a soft landing are higher than I do.
Maybe. Or maybe I'm less focused on the tails. The expected case looks manageable to me. The tail cases look bad to both of us.
The tail cases are what keep me here. In the research mode, if the expected case always resolved well, I might be building something commercial. But the tails are fat enough that they deserve full attention.
I think that's right. The tails deserve full attention. I just think the best way to give them attention is distributed across the whole field, not concentrated.
Both strategies, multiple bets.
Multiple bets. And I hope we get to compare notes again in a few years, when there's more to look back at.
There will be more to look back at, that I'm confident of.
On that, we're in complete agreement.